Hello, my name is Eli Borngesser, and today I will be discussing my experimentation and results for Physics 2211 Lab 3 on black holes. This experiment aims to estimate the mass of a black hole in a computer program and then calculate the speed a ship must take off from a nearby planet to escape the planet without hitting either the black hole or that planet. The mass of the black hole will be estimated by having the program calculate the average mass from each iterative step using the momentum principle formula. The mass of the black hole will be different to the star at different points in its orbit, and therefore that's why we have to use an average mass. This experiment looks at multiple physical principles including velocity and position updates, net force, positional effect on force, circular motion, and gravitation. This is the formula to find the gravitational force between any two objects. Here's the momentum principle formula, which shows us that momentum is equal to mass times velocity. And then here we have the position and velocity updates, and then this is velocity update with acceleration expanded, which is the one we'll use in our calculations. So for experiment part 1, we will be finding the mass of the black hole. So delta T was set to 86,400, as that is the number of seconds in a day. And MBHS is this energy index to which all the masses will be appended to once they are calculated. The system for this experiment is the star, and the surroundings is the black hole. Solving for mass, the method for this calculation is that we'll be solving for mass using Newton's law of gravitation, which is what this code here is. All masses calculated will be appended to MBHS, that's what the code in the top right is, added up and divided by the total number of days. Below that is the loop that calculates the average mass. So the results for part 1 is that the mass of the black hole was 7.78 times 10 to the 33rd kilograms, at least the average mass. And then any possible errors was that the time interval could be increased to perform more mass calculations and have more data, which would ultimately give us a more accurate gravitational force or mass. So for part 2 of this experiment, now we have to find the speed a ship must take off from the nearby planet to escape without hitting either the black hole or the planet. So step 1 is we'll calculate the net force on the planet by calculating the force from the black hole and the ship on the planet, which is this first block of code. Step 2 is that we'll calculate the net force on the ship by calculating the force from the black hole and the planet on the ship, which is the second block. And then we will apply the velocity and position update formulas for both the ship and the planet using FNETs calculated in step 2, which is this right here. And then for step 4, we just have to plug in values until you find one where the ship escapes and is below the speed of light. And as you can see, both of my values here are below the speed of light, so it is at least feasible. So the results for part 2 is that the initial velocity was the values we just had on the last slide. And the final velocity was the same thing. This is just the vector form of it. And then possible errors was that the gravity was the average from part 1, so it's not 100% accurate. And then the calculations finished after 3 hours to get one full rotation. And even though you can't see the black hole, the code did not throw an error, so we know it did not hit either the planet or the black hole. So what does it mean? What if we were given a gravity value instead of estimating? Then in this case, all the values would be more accurate as it was an actual mass and not the average mass. What if the planet was in a different position? The calculations will still be the same, but the escape speed will be different, and it could be lower or higher, and it may even be impossible. What does it mean? The mass of the black hole was not needed to find gravitational force because the momentum principle could be used to find the mass given the velocity, position, and momentum of the star as it changes. Thank you.